we look forward to your presentation. I just say a little bit about Thrishantha's background, which is really very interesting. He started out in life as an electrical engineer in Sri Lanka, got his first degree there, and then went to Japan and studied robotics, got a master's there and a PhD. And then, obviously, liking that subject, went to the United States and worked as, got fellowships in 3 very important centres: Harvard, MIT, and Johns Hopkins University. So, really strong background in robotics. Then, fortunately for Kings, he came here in 2009. And he's in the Robotics Institute at King's, which over King's is not very well known. It actually has 8 academic staff and it's growing. I learned 34. And when I was a student here in 1961, engineering was an incredibly important part of the college. And it went down almost to 0, but it seems to be growing up in these new fields of robotics. So, Thrishantha is a senior lecturer in that department, and he's going to tell us, why robots are robots. Thank you very much.
So thank you very much for coming. This is very usual to have this kind of meetings in the robotics space. It's medicine. Our biggest conference, and medicine biggest conference is something like 20,000 people. Ours is like 500 people. So today I'm going to talk about what we do here, and then in general, how robots can help us to understand our own body, and how robots help us to serve the industries as well as service industries. So my motivation to develop robots came from this application, which is language detection, and a new one. So that is a robot. It's not a robot, but it's a useful device in Afghanistan. So it just rolls down in the wind passively. You don't have to activate anything, and then it walks over mines and then it explodes mines. So this is North Chapter in Sri Lanka. There's an NGO called the Computation Institute based in New York. So they are doing design science. So now the point I wanted to make is, now this is 21st century, and this is how we do design. And then we have robots and very high technologies to explore water in planet Mars, maybe, but we don't have good robots to do our own language education on planet Earth. So there are reasons why on planet Mars it is something like this, and there are no trees and locomotion is not huge. On planet Earth we have this vegetation, and we're going through this vegetation, and then surviving is not an easy task. So I'm going to talk about why that is the problem, and then what we have done so far to understand the problems we have. So this is back in Sri Lanka. This is me and some of my students in my field, somewhere there. I mean, you can see us like everything here and then very stable, but only I know how I was shaking. And I was sweating and shaking, and I'm terrified. So right in front of me, they can be like, actually that guy is shaking. He said this area is demon, but who knows? The global numbers are like 61 countries are affected by language, and then countries who have finished their wars, like Cambodia, still has what to do. Like it takes about another 15 years to do clearing. And then in countries like Kosovo, they can never finish some parts. Like 1/3 of Kosovo has to be removed. And then in Sri Lanka, the injuries are like 80 to 35 years. Maybe the males and then the females. So this is the problem, kind of problems we are trying to address by developing robots. So that can go into dangerous environments where humans are not suited to go, and then do something very useful. So, but as you can imagine, we have this locomotion problem. How to move like a human. And then in a disaster response operation, let's say, for example, in an earthquake, most of the buildings are designed for humans to move through. For example, that staircase, it is designed for humans. And then you cannot have any random robot to climb up those stairs. So because they're designed for those steps are designed for humans. So you have to have human looking, or at least like bipedal robots that can climb up those stairs to look for somebody stuck inside or something. So that is our problem. Most natural environments, any robot can go, but man-made environments are designed for humans, and then a humanoid robot can go. So I think our dreams are like this. The Ex Machina is moving, so you can see that very elegant looking robot. She can, yeah, she is just like, okay, you cannot do this. Can we get the sound? Okay, so fine. So this is the real situation, right? So this is the DARPA Grand Challenge. So the world, the US Department of Defense robotic. So these are the top robots from the top universities in the whole world. So see, like some of these are like behaving like drunk people. Like this MIT. I mean, it's not a job. So MIT is a massive group. So that's it. So what is wrong? And NASA did propulsion lab. It's so so sad. So that is NASA Jet Propulsion Lab. And then MIT, Carnegie Mellon, and then we were the only British team to qualify for the first round, and then we couldn't go beyond that. So King's was the only British team to qualify. So, and that's as far as we could go.
Where's your robot?
Oh, no. Before that, we came. Oh, right, okay.
Do you want to
oh, yeah, it's
I could sing, but
yes, so I think that's fine.
I'm sure we've got them eventually in mind.
Oh,
It's not up to me.
What's that anyway?
Alright. So then, so a humanoid walking can be modeled like that. It's basically an inverted pendulum. If you push it, so it tries to balance itself. And then the human is the same. Right? So from the hip joint, it has to develop these muscles. It's something like this. Two springs, and then there's inverted pendulum, and then the car is like, you can see, like walking forward and backward, and then these two springs, like the muscles here, like to balance itself. So, like the pendulum dynamics can be derived very easily, and then using a very simple controller, we can stabilize it very quickly in 2 seconds. But in a humanoid robot, this is not so simple because there is so much noise coming from the ground contact. And then that is trying to propagate up, and then that destabilizes this whole thing. So I think this is IIT motor brand. So you can see that it's a flat feet, and then little bent knees walking. I mean, this is the best they could do. So without that, they cannot stabilize this robot. Okay, so sorry. So this is the winner. So the only robot that won the competition was Korea Advanced Institute of Technology, PICE. So they won this competition, beating all the competitors in the world. So still, you can see they have bent knees, and then it thinks a lot before making a movement, but they won. And recently we had a big robotics conference, and then the team who made this robot was invited to give a keynote speech at the high speed. So one thing they said was very, very important. They said we didn't do closed loop control, which was very unique. Closed loop control is like you wait for the sensory signal and then do the processing and then compute a descending command and you go to the muscles and then do that continuously. So open loop control is like you have some kind of internal model of your body and the dynamics, and then you just keep sending whatever commands without waiting for any feedback signal. You can take the delayed feedback signals and then update your internal models on the code. So that they said that is the unique thing, which is really, really important for me, because we also believe that type of control is done in all human motor control. Because if you take the sensory signal from the fingertip to the brain, it takes about 120 milliseconds to reach the motor cortex. And then in the motor cortex, roughly about 50 milliseconds of computing, and then again the motor command takes about 100. It's about 300 milliseconds loop. You cannot, if you simulate these dynamics, you will see the hand will shake. So it will work like a system of communication. So essentially that is really happening in a system of communications. So we have to have feed-forward control. So how do we get? So this one example where we need that kind of models. So if you take a wheel and a leg, so you can see a wheel always deforms the soft terrain in front of it, making a reach against it. So it is making its own problem, right? But whereas the legs push the sand against it, behind it, and make use of that reach to move forward. You would force constructing. And then this leg is really done wide. I mean, most animals who walk from soft terrains have legs, and then they are very efficient, not wheels. But this has to be shorter. Wheels have relatively smooth, continuous force profiles. You can predict very easily. So the next force is relatively in the neighborhood of the previous force. But in the legs, you can have fatigue. So one force here, and then the next collision can be totally different. And then they are punctuated forces, and then these like high frequency forces propagate along the body. So this is the best kind of robot you can make. This is definitely Thrishantha. So this kind of wheels and leg combination that was really useful. All the other robots were tested. So this doesn't have that problem of center of gravity, it is not equated to it. And then the good thing is you can go through this soft brush without damaging, without even leaving a trace. So wheels would have definitely damaged the soft vegetation. Let's go. So that is so okay. So let's look at the biological sequence. This is a dead trout. And then this dead trout, if you put it in a tank and then open a water stream against it, so when the water stream starts to flow, something strange happens. So it starts to swim like a live fish. Right? So it goes very up and then I think maybe it goes down at some point. Yeah. So it behaves like a live fish. What is happening? This is the most important point. Computation happens outside the brain. So computation for locomotion happens as a circuit that is made up of the environment and the body. So if your environmental statistics, the water turbulence and the softness of the body matches, that circuit completes, and then that starts to do a computation that really helps the locomotion. So, like you can really take out the brain, still that circuit works. The brain is just doing some tuning of the parameters. It is not really doing active work such as that. So, are our robots using this natural principle? We are not. We just give the full burden to the computer to do feedback control, and then that releases something. So you can really leave it to the body and the environment to solve the problem if you know how to design the world. Right? So that is the key thing about this. And then if you look at other biological, so this is octopus. It can camouflage like that, and then it can go real thing in water.
Dr. Cameron captured this about 10 years ago. He was doing a study in the Caribbean and he was following this octopus for about an hour. When it crept behind the rock and went into camouflage mode, he
Jammed the camera down right in its face, so to speak.
prompting it to go from camouflage to a startle defense.
Blanching white very quickly.
And then eating him.
But I followed the animal and finished the bog after I caught the surface. Was only about 5 feet deep. Screamed like murder, and they thought I was going to die by accident.
When actually closely at squid skin. The idea there is
Go. So when it comes out, so see how floppy it is. On land, it is not that intelligent. It behaves very like that. So the fluidic environment, the buoyance, and everything matters in the computation. And it is not really the brain doing a lot of things, it's the body and the environment working together. So these principles are really important for robots. So if you look at coming back to humans, so here Homo sapiens, their locomotion imaging efficiency is much higher than other primates. So their metabolism is very much the amount of oxygen that is used to walk is very much lower than other primates. So that gives us some kind of motivation that bipedal upright walking is inefficient. So if you compare with robots, so this is something. So in heel strike, so you can see, so the pressure profile, the pressure heel goes from the heel to the toe like that, and then see this continuous force. So that is what is really forcing this direction. So if you could focus, and then there is a smooth profile, but most robots don't do that. Most robots do the heel first, and then most humans do the heel first, and then that causes like a discontinuous force propagation throughout the body, and then that destabilizes the body. Though it is really energy efficient. So we want to get both energy efficiency of locomotion and stability. That is the mathematical problem we are having. So some work done at an Illumina's lab at Cornell and MIT where I was at state lab. So this kind of walk, this thing, I want you to see this robot. So see, so this robot doesn't have a single motor. It is not activated. It doesn't have a single sensor. It is not doing any type of control. But it walks down a ramp. Right? So this is what I said. I said, if you have the body right, it can walk down a ramp just a little bit of energy change. So this robot is the closest robot we have with the energy efficiency of a human. So now you can see the human is equal to a robot without motors. So all of the robots are like 100 times, 1,000 times, like consuming energy compared to a human. So that is the problem. So in a human walking, so there's a thing called metastability. So so you can see this robot. This robot. See, so it can just passively walk without motors on a treadmill, but it walks sideways, and then its center of gravity moves like that. So we call the thing called metastability of locomotion. The robot walks like that, even a human walks like that, but there is a finite probability that it can jump over to the other side. That is causing instability. So it's most of the time it is stable, but sometimes that can be unstable. So a big mistake we are doing in robotics, most of the time, is we are forcing the robot to stay around here most of the time. But whereas the humans, we walk with the knowledge that I can fall, right? So I know I can fall, but I don't really care. So I take it easy. So most of us don't do that. And then they really squeeze everything possible to make it super solid. And then they consume a lot of energy, and then they can go out of control again. So did you notice in the DARPA challenge, one robot was shaking? That is what it did. If you miss something, and you start to shake because the controllers are trying to blind. So, but a human, let's say you ride a bicycle and you're trying to fall, you will just throw the bicycle and jump away. The robot would keep pedaling till the last moment. So that's the problem. So we are trying to understand. So at MIT, I did this simple experiment. I just rolled down a rimless wheel, which is simulating, which is the best approximation for leg locomotion. So in leg locomotion, one leg hits the ground after another, and which is like a rimless wheel rolling. Right? So this lady walking down the ramp, it is just like a rimless wheel rolling down. So you can approximate, understand leg locomotion just using a rimless wheel rolling down. For about 1 year, we collected data rolling down this rimless wheel down the ramp, and then we collected data to see what is really happening so then this experimental data, the 3D motion capture data, we replotted. This is not simulation, this is just replotting the experimental data. And then what we see is these flips, and sometimes these reversals happen. And then if you do trials like 50 trials, and then you closely see one trial after another, nothing repeats. Nothing repeats. Even if you start the luminous wave at the same location, the zero speed at the beginning, same location, same orientation, you cannot repeat two things. By go far, you can go on, and then they will have these things. So see carefully. So when it rolls down, whenever it hits the ground, it jumps down. So it jumps down, the speed goes down, and then gathers speed when it falls, and then loses speed when it hits. So these dots correspond to each point of collision. They are not in the same location. They are not in the same location. There is variability. And then this variability is what is causing us some failures in slipping or falling. In robotics, we try to force these dots to be in one cluster. That is really causing a lot of inefficiency. So now we are thinking of ways to develop new type of controllers that relaxes this thing, and then you allow it to kind of wander around a little bit, but keep in the shape. For example, it's like a waterfall. So if you zoom into the waterfall, you don't see any pattern, right? So water droplets just move around all over the place. It's total chaos. But you zoom out, the shape remains, right? So as far as there is gravity, and you can have local bouncing off and all the chaos, but if the gravity outer force is there, it will keep the shape. Right? So this is the approach we are taking now. Yes.
Can we interrupt the questions?
Yeah, sure.
I've got two quick questions. One is, it's not clear to me what the explanation of the vibration is, because the vibration implies a to and fro, backwards, if I can understand what vibration is, something to and fro, whilst you make progress or not, as the case may be. So what is causing you said it was something to do with feedback, but what is causing the reversal?
Okay, there are two things. So one, that vibration. Vibration is like, let's say the feedback signal goes to the controller. The controller takes time to control, and then by the time it sends the command, due to the dynamics, it has moved to a different place.
Yeah.
And then it sees a big error, and then it tries to correct it. And then it swings back.
I see, so it's a correction.
Yeah, it's a correction.
The other thing is, I just want to say again, when I was a boy in the 1950s, I had a toy which could walk. It was a cow, and it had 4 legs. And if you put it on a slope, it walked perfectly down the slope. I still got it. I can bring it in. I'm just astounded that we seem to have been able to design this toy in the 1950s to walk down the slope. And we're somehow not much further on with 2 legs than we were with 4 legs 50 years ago.
It's not the end of the story.
Fair enough, but
Yeah,
I suppose what I'm interested in is what you don't say, or you haven't said yet, is what you are modelling this on. Because it looks like it's model a human walking on 2 legs, but I don't see much sign of that. There was a wonderful paper written by a man called Lord Graham, who was professor of neurology at the London Hospital and then president of the physicians. And it was a wonderful deconstruction of what you needed in order to move from 4 legs to 2 legs in evolutionary terms. And it's a very detailed analysis of the shift in weight and dynamics and the neural the neural background, the predicate, or the antecedents. Because you've got this problem of how do you adapt and how do you change, whilst at the same time still being able to walk on four legs and you're trying to walk on two legs. I mean, trying, of course. So the question is, what? So
Say that again.
Okay.
Say that.
I'll take it.
So, yeah. So we model. So the reverse wheel, and then we model the soft ground as a spring diaphragm system on lateral and regular direction. So with this you can explain C reversal, and then with this you can explain bouncing. And then with experimental results, the black line is experimental curve of the speed of evolution, and then this red magenta and blue lines are simulated model. So what we see is with the distribution of the friction coefficient, little 0.3 to 0.5, the complete model is off the experimental results. And the coefficient of restitution distribution, restitution is like, so when you hit on something, it bounces back. So that bouncing effect, if it is slightly different from one point to another, that causes a lot of variability. And then if you can model while walking, then you can predict what might happen. And then you can have that internal model and then just use forward, like without feedback control you can walk. So what we are, like in summary, what we are saying is, if you can have some kind of a real-time estimation of the environment, you can have a mathematical estimation of the time to failure. We call it mean plus passage time, so expected time to failure. If you have a rough estimate of the estimated time to failure, and you can explore different actions like wobbling and changing the stiffness of the body and things like that, and then estimate whether that failure time comes closer to you or go away from you. So all what we do by walking is to postpone my failure time further into the future. As far as my failure is in the future, I'm never going to fail. So that's the thing. You are going to fail, but you're going to fail in the future. And that is all these trips into the future. So that is the mathematical formulation we have. Okay. So we call it metastable walking and then dynamic adaptation. So some students
It's spontaneous about
I'll talk about some PhD students right now. Max is trying to understand the role of the variable damping profile is an injury, and then how that affects our efficiency of locomotion. So what we do is that, so we know that this friction profile is different. We program that in the artificial language using the reference space. So the ground can be controlled, so we can simulate any stance conditions or any soft stick terrain conditions.
Thrish, could you turn the sound off? I can't hear both sounds at once. Sorry.
So, yeah. So this friction profile is not constant. So it is varying. So we wanted to understand whether that contributes significantly to the efficiency of locomotion. For example, when you walk to a beach, you might bend your knees a little bit and then control the stiffness of the joint so that just the body walks stably and then you don't have to really think about that walking. And maybe when you're riding a bicycle on a bumpy terrain, you might stand up and then use your knee joint to do the balancing. Or when you're walking upstairs with a coffee mug in your hand, you're not really focusing on controlling the coffee mug. You just ask this elbow joint to have some kind of a spring and a damper, and then you set it there, and then it stabilizes itself. You don't worry about it. So that is what we are trying to model here. And then what we saw was very interesting. So we got that ringless wheel, that robotic setup, to learn a variable damping profile over time, driven by the friction forces. We don't set it we just ask it to experience the collision process and then evolve your own variable damping profile using a linear backpropagation rule. What we saw was a flat damping profile evolved to be a variable damping profile, and then with that the collision forces smoothed up significantly. And we didn't ask it to smooth out the force profile. We just said, just minimize it. And then with that, the speed grew. The speed profile started like that, and then it went up. So what does it mean? So if you have the force multiplied by the speed, you have efficiency gain. So you have locomotion efficiency gain just by adapting a variable damping profile over time. So that kind of says something about the nature, why it is variable. And then some undergraduate group very recently did some interesting experiments. They set different stiffness and damping conditions for the industry, that is the knee joint. And then they looked at how the velocity profile looks like in the long term. Like they set it to run, and then set it to settle down to some speed. And then they saw at different spring and damping settings, they have different steady state velocity profile. That means just by controlling your stiffness and damping, you can migrate in the state space without controlling the state space directly. For example, so I have about, hand has 7 degrees of freedom and another has 14 degrees of freedom. The body totally more than 30-40 degrees of freedom. If I try to control in that 40-dimensional space, it's massive. Let's say I walk to a beach and then I think about 40-dimensional space to control, it's massive. But if I just worry about the stiffness and damping, 2 parameters, and then I set it, and then I start walking. But I don't really worry about the speed and the way I walk in the beach. It just settles down to some pattern. I don't care, as fast as I can walk. So that is what we can learn from this experiment. So then, with those insights, we developed soft robots that can walk like octopus or things like that. So, I mean, soft robots is the great thing about soft robots is they can absorb a lot of forces, collision forces, and the punctuated forces I mentioned. So they can go stable like that. And they can absorb those collision forces and then dissipate in their damping, in their body damping. So that area is really now growing in our lab. So there's another PhD student, she's from Ecuador. She is thinking of developing robots for Ecuadorian farms to do weeding, and her inspiration is coming from this girl. So you can see these girls, they have amazing ability to walk on tricks without falling. So can you imagine? So it does, it's very acrobatic. And kind of peaceful. So her question is, what makes these girls so amazing? Is it the brain? Is it something to do with their body and something to do with the hood? So as usual, we start with the most primitive structure, which is the hood. Without a brain, without a single sensor, without any kind of control, we just rub against different structures. So what we see, there's some vibration there, and then the other one did not, because we locked the one joint, and then we looked at, we lock each degree of freedom, and then we do experiments. So we can lock this stretching, we can lock this joint, and then 9 degrees of freedom. What we saw was this. So if you have just a round foot, and then you rub against that brick or something, that's a brick we are doing. So the work we had to do was rub it against a full stretch is this much. And then for rough terrain and smooth terrain. For rough terrain, so the scale is off, like this is very hard. But there's high variability. So look at all other things, the group, you can reach one by one, and all of them roughly at a high level, but like about 3 times high. 3 times high, no, it is 4 times. Work you have to do to push it against the thing. So what is it, why is it so stable? So it is a passive dynamics of this group. That should kind of embraces that ground and then resist movement. Just that passive structure. So maybe the brain is doing something, but see, just the hook is helping the whole body to increase its stability by 4 times. Just the hook. So and then that way, maybe the next step maybe getting the hook to walk just like before. And then we will see that at the end, our prediction is we will come up with a robot with a very simple controller and a very smart body, and that suits the environment. So that is our way of designing robots. Starting from the very bottom, very primitive structures, going to the controllers later, rather than coming up with the whole body and then without understanding what it is and then doing massively complex controllers. So this is another slide. So she is trying to understand this how humans interact with the environment through this kind of hard structures, hard frames. So this is a dog guiding a human using a hard frame. So this maybe if we get some inspiration from this kind of scenarios, maybe we can develop a robot to guide humans in a fire or disaster. So I said like we need robots to guide people in a natural disaster or something. So locomotion is one problem. The other problem is to have human-robot communication. So we did experiments using human guiding in a natural, man-made environment, so that the robot will have to go in this environment, guiding a blindfolded human using this hardware. And then we collected data of hand movements and then the human orientation data. And then we fitted with the auto-recursive model, and then we found out that this auto-recursive model, this guider predicts the error of the follower into 3 steps into the future to conclude the current action. And basically, he's building the internal model of the follower to guide. So even the dog, so I blindfolded myself and got a guide dog to take me from the guide dog association to Houston Station, and then come back. I went to the train and blindfolded myself. I felt so comfortable. I mean, the first few minutes was very kind of tense. I didn't trust the dog, but quickly I built some trust in the dog. And then somebody was following me, and then she said, there was a low-hanging branch. So, the dog can go underneath that. But the dog avoided it, because the dog knew that I'm going to hit that branch. So definitely, the guider is building a dynamic model of the follower, and even a kinetic model of the follower, to make guiding robots. So, and then we saw another interesting thing. The follower uses 2 commands in the past to take the current step. That is, it is a second order reactive model. So it's reacting to the guider, and the guider is a predictor. So we can export that mathematical model to a robot, and then now we did some experiments, and we found that it can do about 4 seconds step. Within 4 seconds, it can correct a human movement error, about 60-degree error to 0. And then we saw another thing. So we model the follower as a virtually damped inertial model, and then we looked at its parameter variations when it takes 90 degrees, 60 degrees, and straight lines. So these correspond to different thrust conditions. Like, let's say somebody is taking me in a 90 degree turn, suddenly I lose confidence, I lose trust. And then what happens to my physical movement if I lose trust? That was the question. So what we saw was nothing changes much except one parameter, which is the voluntary virtual damping coefficient. So in the voluntary movement, the damping coefficient only changes when I lose trust. So this is the first time we found a psychological state like trust can be measured using a physical variable, like a damping function. Voluntary damping in the voluntary walking. So then the robot can monitor this parameter and then understand the psychological state of the follower, so that the robot can slow down when the trust level or confidence goes down, and then it can accelerate when the follower is happy. So because it knows its happiness level using just a measurable parameter like that. So this was published in class, and this was short work. So Lisa's work. So we are working with the Guy's Hospital in interaction experiments, like so when surgeons do cancer location, tumor location, palpation experiments. So these are fingers, so these are cancer or the tumor and soft tissue. And then what happens when we palpate the soft tissue is we saw that two classes of surgeons use two types of palpation. So this is the force and this is the velocity, and then we saw clear force velocity modulation control strategies of these surgeons. So this means the behavior and the environment recognition is just common. So this is true for walking, this is true for palpation, this is true for any kind of interaction. We saw that we had did trout experiment and then other robotic experiments. So then we implemented that strategy in a robot, and then we saw something very interesting. So what we saw was if there was no tumor in the soft tissue, it liquefies the tissue. It goes below the nominal stiffness level of the tissue. You feel it softer, right? And then, but if there is a nodule, it becomes harder than the nominal stiffness. So, for example, nominal stiffness is there's a tumor, there's a tissue, and you just press against it. You feel something, and then you do that palpation strategy. Then you feel there's a harder nodule inside, right? So the behavior and the tissue coupling is really interesting there. So now Nantai is doing some more work on that. So his hypothesis is, so for example, let's say like when somebody is asked to pay an object, so they just walk it up and up. So they interact with the environment. It is not a static measurement. So they interact. So while walking, I estimate the walking, the ground, for instance. So over samples. So then I go back and down, and then I estimate the environment all the time actively. So what is happening here is like our model is like these tendons and the spindles are in the actuator. That is the difference between robots and humans. In humans, the actuator and the sensors are in the same tissue. So when you take action, you change the way you feel the world. And then in that coupled system, it makes it easier for people to estimate the environment. So then to test that, he developed a robotic finger, where he can control the stiffness of this joint. And then by controlling the stiffness of that joint, that nodule, the way it feels, we found that the way it feels is different for different stiffness conditions. And then we got human participants to palpate these things, and then we recorded their EMG muscle activation strategies. And then if we implement those muscle activation strategies in this variable stiffness joint, what we see is something like a big improvement in the detection accuracy. That can go up about 90, more than nearly 100% accuracy of localization. just by implementing the human strategy in the robot. And then this way we can test different hypotheses about what the humans might be doing in robotic counterparts. So then, I mean, that's a very, otherwise there's no way we can test. I mean, the brain is involved, the muscles are involved, so many tissues are involved, there's no way you can separate one thing from the other. So this way we can clearly separate and then say, okay, this is the measured variable and this is the hypothesis, and then we explain what is happening in the human behavior. So this is, how much time do we have?
5 minutes.
About 5 minutes, I'll close. So this is quickly another PhD student who graduated recently. So his question was that how do we hold a hamster? So a hamster, if you do to a robot, like it will squeeze and kill it. So this is our hamster. So it's a bicycle tube, and then we randomly deflate and inflate it, and we get the robot to control it using a very simple controller. What it does is it predicts the probability of failure in the future, and then if the probability of failure goes down, it relaxes the bit, and then if the probability of failure goes up, it increases the bit. That's so simple. And then that was our hypothesis about what the human brain might be doing. The thing I said, the mean per spatial time, the time to failure prediction. And then if the time to failure reduces, that means if it comes, the failure is imminent, then you take action. Otherwise, you relax. Just keep on doing so. So what the robots usually do, okay, so there's this tight grip, and then if the hamster tries to escape, it will squeeze more. Right? So maybe squeezing will make it struggle more. Right? So you can just relax and then it will stay sometimes. So that is the approach, the different approach we are seeing. The environment can be used. You can get the environment to help you by relaxing the hamster, for example. That is like I'm finishing. So the robotics journey came from 1920s, like in the early 19th century, people talked against slavery, and then Sojourner Truth is a big advocate. She was a slave, auctioned several times in her life. And then she gave a big speech in Akron, Ohio in 1851 called Ain't I a Woman? It's a big, and then Abraham Lincoln used his third point in his abolitionist movement. And then NASA, the Jet Propulsion Lab, the first robot it sent to space, it named the robot after my name, Sojourner. And then in that, NASA said, so the Memorial Park, and NASA said they are doing the same thing. Sojourner fought against social gravity, and then this robot is going to fight against planetary gravity and go into the free space. So they are doing the same thing, and then why not name that after that? And then with these inspirations, Carl Popek, he wrote a drama called Rossum's Universal Robots in 1921. That is the first time the word robot was coined. In the Czech language, it is worker or forced labor. And then he said, in the future there will be robot machines that will look like humans. And then you can get all your dirty work done by the robots and then just release these humans. So, and then it came, and then today we are here. So this is another project we are involved in. Most service robots we see today. So this is a project we're involved in. So in industry, today the industrial robots are programmed. If something pushes, somebody pushes that thing, they cannot figure out how to do it. We can make those robots more intelligent like that. Like if the environment changes, they can reconfigure automatically, and then we think about it. And then even more, we got another robot to help the body robot. If somebody pushes that thing, and then the other robot comes and helps him, right? So this was the European Union funded So this is the latest, maybe state of the art of industry.
Science fiction not long ago now by
Some other people have been.
service, for example, by taking over logistical tasks, provide all-round support with care, and enable handicapped people to regain mobility. The platform for automated production processes is exhibiting not only innovations in robotics that will lend people a hand in industrial processes as well as in daily use. I can be surprised. The humanoid has 48 engines. The movements are controlled by wires. The skeleton was created entirely in a 3D printer. Of course, Roboy can also interact with his counterpart. I'm so shy. I always say Roboy's development is finished when I can put it in a kindergarten for a week and get him back in one piece. This is certainly the next step.
So this Kings is involved for the next head of what is the Kings? So he is involved in the project, so we are building a soft robot inspired by the octopus to do surgical, the minimally invasive surgery. So this robot is Himalaya compatible. It has all the soft sensors inside, the force sensors, the bending sensors, stiffness sensors, and this is now radically changing the way we do minimally invasive surgery. I think you know about the Da Vinci robot, which is like just 3 sticks going laparoscopic tools. That the workspace is very limited, right? So you cannot go around organs and then do surgery. So with this, you can just go around organs and do surgery. So yeah, that's it. And thank you very much for coming. And this is my team. Thank you very much.
Thank you very much, Thrish. As I mentioned at the beginning, I thought we might have a very good, interesting, very different lecture, and that's what we had. So what we do normally is just have a couple of questions here, then we go upstairs and have some mince pies, and those of you like a glass of wine, perhaps a glass of wine, and you can continue to ask Thrish questions. But we'll take a couple of questions down here. Here's one, Richard.
So big difference to me, and I can't put my finger on it, is the idea of prediction failure rather than prediction error. I'm quite used to the idea of predicting error as a way of learning in the brain, but predicting failure is much broader anyway. Is that something you're saying?
Yes.
It doesn't really matter about the error, just worry about the system fails, and when you get close to it. How does the robot sense when it's going to drop the hamster, or get a sense that the failure is going to happen? How does it know it's approaching points of failure unless it's learned that in the past?
Exactly. So that's really the center of the problem. So what it does is through interaction, it collects past data and then constructs a probability distribution on the road. And then if you have a probability distribution, and then if you know, let's say the x-axis is the force, and then the force variation has some kind of distribution, and then you can compute the probability of reaching a critical force where that causes some failure.
Does it have to fail?
No, it doesn't have
slippage or
yeah, it has never failed so far.
Right.
And then but the micro failures, like for example, the hamster slips slightly.
Yeah.
Then I know the force at which, my tangential force at which it slips. Right? So when I walk, I do micro failures, I do slips and slip reversals. That is enough for me to understand, okay, this is a slippery terrain, this is a slippery floor, this is rolling, or something, but just micro failures are enough for me to construct the distribution. And then make a prediction that, okay, if I walk like this, in about 2 seconds time, I will get into this way. It doesn't have to be in 2 seconds time you have to fail, but it's expected time to fail. Right? It's just the average time to fail. So we can compute that real time, that now we know the math to do that. And then the important thing is, if that 2-second window drift towards you while you are walking, that means like it becomes 1.5. Now I have to take action. I have to slow down or I have to do something, right? And then when I slow down, let's say that expected time to failure goes to 2.5, then I did the right thing. So that is the feedback we are getting. So if it goes 1.5 to 2.5, I can keep on relaxing and walking at that speed.
So there's now a feedback element, which is
Feedback
working
element
on the model rather than on the actual
Yeah.
sensation of
But with a massive reading space.
yeah.
So rather than an error feedback, which is next sampling interval.
Yeah.
That is why robots start shaking. So because in the next sampling interval you are different, you are somewhere else. And then you get feedback in the past, which is no more relevant. So this type of control has to be radically changing. So it started at MIT when I was there last decade, and then we were at quantum, and then motion dynamics. I couldn't show that video here, but the big dog. So now we can walk on the snow, right? So you can walk on snow. It's really stable. So the topic I put, like why robots hate beaches, it's not that they cannot walk, but it's really difficult to predict the movement process like on sand. So because it's grainy and there's no homogeneity, and then it's very difficult to construct that over the snow flat. And then it's multi-model, it is not single-model, and then it's very difficult to predict. But still, yes.
I'm a simple biologist, I might get this
Very simple.
I tried two things together. One time, a fascinating slide you did showing the difference between a wheel distorting sound, producing problems for itself, and a stepping system where the distortion actually helps. We've got something called shift. So saw that. And then you also took a different part of the presentation about the fact that if you're designing a robot to move in a human adapted environment, so spiral staircase, it's got to be bipedal to get up there. Thinking more broadly in biology, I suddenly had an image of using films of sidewinding snakes moving through sand. So if you're stuck, if you're on the surface and you're distorted, it's like a moving version of the foot distorted the sand. If you push against the back groove.
Right.
So it would sidewind the robot, work through soft sand. It would work on an environment lots of bits in it, your cabbage wheel, it would have perfect except for push against those. It would have problems with a hard, shiny surface. But if it had a surface like the ghost foot, it would work even there.
Yeah.
So I wondered if anyone's looked at sinusoidal motion in a robot.
So, Howard Joseph at Carnegie the Robotics Institute, he's the world authority in the snake slavery. So he did a number of experiments in tree climbing and then going through sand, and then somehow he ended up with surgery too. So snake robots for surgery. And I can go through narrow gaps and find its way through. Slithering is really, again, it is a continual motion, continuous version of walking. It is just pushing against the ridge and then moving forward. And then the slithering, the sinusoidal also, they do phase control, the frequency control. So sometimes the snakes can do very high frequency, like wavy movements, and that can go pretty straight sometimes, like very low, long waveforms.
What about upstairs?
Upstairs, there's this iRobot
running with the snakes.
Snakes. So running rooms and somewhere. They can climb up. So it is. I don't know if you have seen the Spirit rover, the planet Mars still running there. it is using a mechanism called the Rocker-Bogie mechanism. So snakes can easily realize that Rocker-Bogie mechanism. Rocker-Bogie is a kind of discrete thing, but snake can do that with their brain. It's a very versatile brain. Yes, so that is why snakes and that kind of animals survive even in water. They are great swimmers. Yeah.
Okay, let's stop there, and I'd like to thank Thrish once again for a really excellent talk. But if you'd like to come upstairs now, and hopefully Thrish will come up with a continued discussion, and you continue to ask your questions. That was really great. Thank you. Very difficult.
That's fine. It's not like
related to movement, science of memory, and you know that's they should all come up there too.
I was going to ask the same question, should you central gravity as well? Should that be your certainly it sounds quite to get that, it's just like way down to the